Today we will be talking about chemical shifts, what is the origin of chemical shifts, and the idea of today's lecture is to give you an idea of how powerful the technique of NMR is in all kinds of materials and chemical characterization. So in the previous lecture we looked at the carbon-13 spectrum in ethanol. Two kinds of carbons. The peaks are separated by a certain frequency difference due to the effect of chemical shift. We don't know what's the origin of this chemical shift. Nevertheless, we know that the different carbons, the alpha and beta carbons in ethanol, they occur at different LUMS frequencies. And the separation between these frequencies, as evidenced in this spectrum, is about 2 kHz. Now this spectrum is taken at a LUMS frequency for TMS of 50 MHz. That is, if you put TMS in the spectrometer, it will resonate at a frequency of 50 MHz. So TMS is being used as a reference. Now if you take the same sample and put it into another spectrometer which has twice the static magnetic field and hence twice the LUMS frequency of the reference compound, 100 MHz, the separation between these peaks increases. The chemical shift increases even though the final structure of the peak remains the same. And you will also observe that the height of these peaks or the area of these peaks will also go up because of the sensitivity dependence on the magnetic field squared, as I explained previously. Now here the separation between these peaks has doubled to about 4 kHz. So this means that every spectrometer will have its own frequency axis. But in order to calibrate against a common reference, this frequency scale is normalized, and it is normalized in the following way. So we take our LUMS frequency of interest, omega naught. From it we subtract the LUMS frequency of TMS. So this will give you an absolute frequency difference. And of course this frequency difference will depend upon the LUMS frequency or the strength of the magnetic field. However, if you divide this difference by omega naught TMS, you will obtain a frequency which is normalized, which is unitless, and that is called delta. And the units of delta, now delta is such a small number. Delta is such a small number because omega naught is so close to omega naught TMS that this delta is a very small number, and it is often mentioned, it's always mentioned in units of ppm. Now as an example, in the top case, the frequency difference.
Sir, ppm means that you multiply delta with 10 to the 6?
Yes, with 10 raised to the power 6. Or you divide by 10 raised to the power minus 6. अच्छा, मैं एग्जांपल देता हूँ. अब पहले वाले केस में the frequency separation is 2 kHz, that is 2000 Hz. That is the frequency separation. Now if you divide this frequency separation, which is in absolute units, with the LUMS frequency of TMS, which is 50 MHz, so in order to convert a frequency difference into the delta scale, we just take the frequency difference and divide it by the reference frequency. Okay? And this turns out to be 40 ppm or 40 to 10 raised to the power minus 6, which is 40 ppm. Now if you take the bottom spectrum, the frequency difference is now 4000 Hertz. You divide it by 100 into 10 to the power 6, again you get the same number, 40 ppm. So the frequency difference between, or the chemical shift associated with the two kinds of carbon nuclei in ethanol is 40 ppm. And this mention of 40 ppm is independent of the spectrometer on which this spectrum was acquired. Now this is an example. The same spectrum, when it was plotted on an absolute frequency scale, absolute with respect to a transmitter frequency. This is really not plus 2000 or 2500 Hertz. It's referenced with respect to the transmitter frequency. Okay? It's the offset frequency. But nevertheless, it's an absolute frequency difference from the reference frequency. But if we divide these frequency scale or normalize it with reference to the TMS lambda frequency, we get a scale which is called the ppm scale. And the ppm scale, on the ppm scale, the difference is almost 40 ppm. So you take a spectrum on a 10 megahertz spectrometer, 500 megahertz spectrometer, 30 megahertz spectrometer, the frequency separation or the chemical shift between these two kinds of carbons will always remain 40 ppm. Now the convention in plotting the ppm scale is that the ppm scale increases from right to left. So the ppm scale is increasing as we are going leftward. This is a universal convention. अब इस convention के बारे में हम मज़ीद बात करेंगे आज के lecture में. अब आप ये देखें कि there are different kinds of organic. There are millions and millions of organic molecules, and they're characterized by functional groups. Now, when you have an organic molecule, for example, a methyl group, it's a functional group. The protons in the methyl group will generally occur at a certain place in the ppm scale. That is between 0 and 2 ppm. The methylene protons will also occur more or less in this region. If you take the aromatic compounds such as benzene, the proton in the benzene will resonate, will have a LUMS frequency around 7 or 8 ppm. The aldehydic group protons will resonate here. The carboxylic acids will be here, and so on. The ethanols have a wider dispersion in the ppm scale, and so do the amines. So this diagram is a general rule of thumb which gives you a qualitative understanding or a qualitative picture that the resonance frequency of a proton will depend on the functional group in which the proton is present. So the difference between NMR and other spectroscopic techniques is there's a single proton, the identity of that proton is hydrogen. The atomic identity does not change whether the proton is in a methyl group or a methylene group or an aldehydic group or an alcoholic group. It does not change. It's the same isotope. The element is the same. So mass spectrometry will not distinguish between a proton that comes from a methyl group or a methylene group or any functional group. It is oblivious to the identity. However, the real power of NMR comes in telling the environment of the proton inside the molecule. So NMR is a chemically specific technique, and it tells you not only the overall molecular structure, but it also tells you where inside the molecule is that particular peak coming from, or what is the local environment of that proton inside the molecule. So that is the real power of NMR. It tells you the environment of the hydrogen atom or the carbon-13 nucleus or the nitrogen-15 nucleus or the oxygen-17 nucleus or whatever NMR active nucleus you're talking about. Where is it present inside the molecule? So that property is sometimes called the chemical specificity So NMR is a chemically specific technique, whereas mass spectrometry is an elemental analysis technique. ठीक है? अच्छा, अब हम example spectra देखते हैं, मुख्तलिफ. अब suppose we have a mixture of different organic compounds. TMS, we have methyl cyanomethane, we have acetone, we have dimethyl sulfoxide, and we have benzene. Okay? DMSO is generally used as a solvent in NMR spectroscopy. Right? You need to dissolve your organic compounds in some solvent unless you're working with pure liquids. So the TMS resonance, the Lambda frequency is at 0 ppm on this scale. And look at the scale is increasing from right to left. So this is a universal convention. TMS occurs at 0 ppm. Generally, you put in a small amount of a reference, for example TMS, or even the solvent can be used as a reference. Everything DMS then goes back to TMS.
DMS solvent would be used as reference.
DMSO can also be used.
Would it give a different?
So it is at a different peak. It is at a different Lambda frequency.
So we would have different peaks for that. Then, मतलब उसके लिए हमारे पास जैसा जो
हमारे पास tables होंगे जो बताएंगे कि DMSO किस frequency पर होगा और कितने pH पर, कितने temperature पर, because it's also pH and temperature dependent. अब देखें ये जो अब ये सारे के सारे जो मैंने examples लिए हैं ना, अब मसलन बेंजीन में 6 हाइड्रोजन हैं और सब के सब इक्विवेलेंट हैं. There is no difference between them. So it gives one peak. DMSO gives one peak. Acetone gives one peak. Right? Similarly, cyanomethane gives one peak. TMS gives one peak. So we have a mixture of different molecules, and the spectrum of each molecule is distinct. So this is a spectrum of a mixture. However, sorry? So y-axis पर क्या होगा?
Intensity of the peak.
Y-axis पर है तो intensity of the peak. वो किस चीज को जाहिर कर रही है? Intensity of the peak.
Concentration.
ठीक है. वो mole fraction को जाहिर कर सकती है. And it's also showing the number of protons in the molecule. ठीक है. So this has 3 protons. This has 12 protons. This has 6 protons, 6 protons, 6 protons.
So, but for example, TMSS.
But which means the mole fraction is very small. The concentration is very small. So the area of the peak or the height of this peak is telling you both the concentration as well as the number of spins from which the signal is coming. अच्छा. अब ये एक और है कंपाउंड. Phenyl acetate है ना ये. ठीक है. So this is phenyl acetate. Now let's see where the protons are. There's a CH3 group here.
I think it's benzyl acetate.
Benzyl acetate. So there's a CH3 group here, a CH2 group here, and an aromatic complex here. Now there are 5 protons here. 1, 2, 3, 4, 5. ठीक है. यहाँ पे 2 protons हैं और यहाँ पे 3 protons हैं. Now this is one pure molecule. This is one pure molecule, and I've taken the spectrum from the website which synthesizes this molecule, the supplier of this molecule. So this is an NMR spectrum of this molecule. Now there is no mixture here. There is really no mixture here. It's just one molecule. But why do we have these 3 different peaks?
Because of different chemical environments.
Because of the different chemical shift. Because there are different types of protons. Even though the identity of the proton, the elemental identity of the proton is the same isotope in each of the 3 kinds of functional groups, but they are occurring at different Lambda frequencies because their environment is different. And the peaks will have a finer structure as well due to splitting. That we will discuss in the next lecture.
It shouldn't be the protons in benzene. All of them are not same. So all of the protons in benzene.
Right, they're not equivalent. But the chemical shift between, for example, this position, the ortho position, there are two ortho positions, two meta positions and one para position. The chemical shift between the ortho, meta and para in this case is so small that it's not appearing on this spectrum. But of course, all the protons are not magnetically equivalent. But the chemical shift is so small. But there are three major groups of peaks. And the ratio of these integrals or the areas of these peaks will be in the same ratio as the number of protons from which the signal is coming. So the ratios will be, this will be 5, this will be 2, and this will be 3. So if you look from here to here, the height is 5 units, from here to here it's about 2 units, and from here to here it's about 3 units. So you look at the integral under each peak, and you look at the relative ratios of those integrals, you get the number of protons from which that peak is originating. This is the first rule of assigning different peaks to different functional groups. Okay?
So what is it? This red line is representing?
This red line is representing the integral. So you go from here to here, you encounter a peak, you look at the area under the peak, the area under the peak goes up, it remains constant here, then the area under the peak goes up, remains constant here. This is a real spectrum, so you will also see noise. Every spectrum is noisy. Alright. Now I will give you a number of examples that show how chemical shift changes and how chemical shift depends upon the environment, upon the structure, upon the geometry, upon the stereochemistry. So the chemical shift is the messenger of where that particular nucleus is in the molecule. What kind of molecule is it? What is the geometry of the molecule? What are its neighboring moieties? So you have a spin or a nucleus. उसका कुर्बो जवार क्या है? Chemical shift इसलिए important है और NMR इसलिए powerful technique है कि वो उस particular spin का या प्रोटॉन का या न्यूक्लियस का कुर्बो जवार भी बताता है. ठीक है. अब फॉर एग्जांपल ये है फॉस्फोरस पेंटाक्लोराइड. ये किस तरह का स्ट्रक्चर है? इसकी सिमेट्री अरेंजमेंट क्या है?
ट्रायंगुलर बाइपिरामिडल.
ट्रायंगुलर बाइपिरामिडल. ठीक है. अब if we look at the phosphorus spectrum, phosphorus 31 is a spin half nucleus. If you look at the phosphorus spectrum and you have the gaseous molecule, in the gaseous phase, or the molecule is dissolved in a certain solvent, such as carbon disulfide, you will get one peak, because of course there is only one phosphorus. However, if this phosphorus pentachloride is taken in the solid form, there is a disproportionation reaction that takes place, and two kinds of species are made: phosphorus hexachloride and phosphorus tetrachloride. Now, if you look at the phosphorus spectrum, you have a spectrometer that is fitted with the phosphorus channel, a probe that can be tuned to the phosphorus frequencies. Then you will see two peaks, because there are two kinds of phosphoruses now. One is chelated by 6 chlorines and one is chelated by 4 chlorines. Hence, the phosphorus species occur at totally different chemical shifts. And look at the chemical shift difference, 400 ppm.
So basically, the environments are different. One is tetrahedral and the other one is bipyramidal.
So I had this question, like, why would it split into this two things when you take it in a solid form, this spectrum? Why does this disproportionation occur?
Because there are two different kinds of phosphoruses now. There are two different species. One is phosphorus hexachloride ion and the other is phosphorus tetrachloride ion.
But we started off with PCl5.
Right.
That has to be, there has to be some chemistry, maybe, I mean, when you place it inside, the NMR, it maybe splits into
No, it doesn't split. So this is in the gaseous form and in the solution form. This is phosphorus. What happens to phosphorus pentachloride in the solid form? A disproportionation reaction takes place. This kind of reaction takes place. So you get two kinds of, so this is a structural change. Two new molecules are formed, and in those two new molecules, there are two different kinds of phosphoruses. Therefore, the chemical shift builds up. Now, look at the chemical shift difference. It's about 400 ppm. So protons have the smallest chemical shift dispersion. On the most 10 or 15 ppm, 20 ppm. But other nuclei, such as carbon or phosphorus or fluorine, give you much larger chemical shifts. And I will ask you the reason at the end of this lecture. Alright, so I am giving you a large number of examples now, just to bring home the idea that chemical shift is a messenger of the environment of the nucleus inside the molecule. Alright, now this is the compound. There are four metal ions. Suppose there are cobalts, okay, and 12 carbonyls. So this is dodeca carbonyl tetracobalt complex. Okay? It's an organometallic compound. Now, if you take this compound, synthesize this compound, you don't know its structure as yet, you can find an NMR spectrum. So, if you take an NMR spectrum of the oxygen 17 nucleus, so this is not the natural abundance nucleus, but still there will be some oxygen 17. So, if you have, if you want to do NMR with a less abundant nucleus, what do? You take the spectrum again and again, again and again, again and again, again and again, and then you add up the spectra. Some peaks will eventually build up. This process is called signal averaging. So if you want to do carbon-13 spectroscopy and you don't have an enriched sample, you can take a normal sample and take do the spectrum, run the spectrum again and again, again and again, thousands of times overnight, and the peaks will eventually come out of the ground. Okay? This process is called signal averaging, but it's time consuming and expensive as well. But if you take this compound, which is take this organometallic compound, you get 4 peaks of the oxygens, which means that there are 4 kinds of oxygens, 4 different environments in which the oxygen can be. Now you have different candidate structures. You can use the NMR spectrum to choose between these candidate structures or choose between these symmetry groups. Now I give you half a minute or a minute to decide which symmetry group does this particular molecule fall in. So this is the tetrahedral, this is C3 with a reflection plane, and this is D2D diameter. Now could you assign a particular symmetry group to the molecule that we're talking about?
I think D2D होगा.
C3B.
So I think D2D होगा, because you have between 2 M's, right? You have CO between 2M in each case, but over there you don't have CO between each of them. So I think for them you would have.
Sir, I think C3B because सबसे ऊपर वाला मेटल है ना, उसके ऊपर जो कार्बन लगे, it is one type of oxygen. फिर जो 2 metals को combine करता है, that is the second type of oxygen. फिर जो नीचे वाला एक मेटल के ऊपर ऑक्सीजन लगा, तो कार्बोनाइल लगा है. सर उन दोनों के 2 डिफरेंट है because the chemical environment of the For example, the सबसे lowest oxygen is different than the one उससे ऊपर वाले लगा.
बिल्कुल सही. So it is C3V. If it were the tetrahedral, the TD,
it should be one.
It should be only one peak because all the 12 carbonyls are totally equivalent. अब इस पर्टिकुलर केस में देखेंगे जो ब्रिजिंग कार्बोनिल्स हैं, ये ब्रिजिंग कार्बोनिल्स हैं और तीन तरह के टर्मिनल कार्बोनिल्स हैं. एक जो अकेले लगे हुए, एक जो पेयर्स में लगे हुए और एक जो ट्रिप्लिकेट में लगे हुए. So there are 4 kinds of environments for the carbon, 4 kinds of environments for the oxygen. So you get 4 peaks. So you can use the NMR spectrum to choose between different structures, to choose between valid physical possibilities. All of these possibilities are plausible, even though there will be different energetics involved. One of them will be a more energetically favorable. So you can do other kinds of calculations or experiments, but NMR is one technique that helps you choose between different symmetric groups. ये पहचानते हैं मॉलिक्यूल क्या है?
Rhenium, tris
Chloro, tri, phenyl.
PPSD क्या ग्रुप था? Rhenium triphosphine chloride.
कौन सा?
Rhenium triphosphine chloride. Rhodium. Okay. Rhodium triphosphine chloride.
Rhodium सबसे लास्ट में आएगा. पहले क्लोरो, ट्राइफॉस्फो, फिर.
So this is chloro, triphenyl phosphine, rhodium complex. So this is Wilkinson's catalyst.
Oh yes.
And what is Wilkinson's catalyst?
Sir, hydrogenation
For
का use
hydrogen.
होता है. कौन से मीडियम के अंदर?
Heterogeneous
medium.
As well as homogeneous medium. Homogeneous और heterogeneous दोनों तरह के catalysis में इस्तेमाल होता है.
Homogeneous ले जाते हैं.
लेकिन heterogenize भी कर सकते हैं. अच्छा, तो देखिए, there are 2 kinds of phosphoruses. One phosphorus is trans to the chlorine and one phosphorus is cis to the chlorine. Now, the trans and the cis phosphoruses occur, they have different chemical shapes. So they occur at different regions in the spectrum. And we will see later, in fact, this is a very good molecule of studying how the splitting takes place. But let's ignore the splitting for the time being. This is one kind of phosphorus and this is the other kind of phosphorus. And the 2 peaks should be in a particular ratio, which is 1 to 2. So you take the area under all of these peaks and take the area under all of these peaks. This area will be twice this area. ये स्टीरियोकेमिस्ट्री में अगर ये देखें तो 2 तरह की, या एक आइसोमरिज्म है, ठीक है. सिस का मतलब जो क्लोरीन के प्लेन में, क्लोरीन और रोडियम के प्लेन में, और ट्रांस जो प्लेन से बाहर.
ये लीनियर नहीं होगा फिर, ये जो क्लोरीन, रोडियम और जो सिस उसका फास्फोरस, ये एक प्लेन में आ रहे हैं, एक कोलिनियर तभी प्लेन.
इसका स्ट्रक्चर ट्राइगोनल बाइपोलर बिकॉज़ मतलब जो क्लोरीन और फॉस्फेट में जो सिस वाला है वो एक ही में होगा, ऊपर नीचे हो.
मेरा नहीं ख्याल सर, हो सकता है ये स्क्वायर प्लेनर हो, आई एम नॉट श्योर. अच्छा, अब आप ये देखें कि ये एक स्पेक्ट्रम है, और एक पीक आपको मिल रही है एरोमेटिक रीजन में. अब जो प्रोटॉन्स बेंजीन रिंग के साथ डायरेक्टली अटैच्ड हैं, ये वाला प्रोटॉन, ये वाला प्रोटॉन, ठीक है, वो एक पीक पे. और ये जो मेथिल ग्रुप्स में, यहाँ पे एक मेथिल ग्रुप है, एक मेथिल ग्रुप यहाँ है, एक यहाँ है, एक, ओके, और ये सारे के सारे मेथिल ग्रुप्स इक्विवेलेंट हैं. अच्छा, तो देयर आर 9 protons in the methyl groups, and there are 2 protons that are directly attached to the benzene group. So the ratio is 2 to 3, 6, 9, 2 to 12, 2 to 12, or 1 to 6. So if you look at the areas under these peaks, the ratio is 1 to 6. So you can unambiguously assign this structure to the spectrum. You can correlate the structure and the spectrum. Okay. So this structure corresponds to this spectrum, and if you look at another molecule, C9H12, in which there are 3 methyl groups, the ratios are now 1 to 3, 3 to 9, or 1 to 3. So you can unambiguously assign this particular structure to this spectrum. ठीक है ना सर? तो हम पीक इंटेग्रल्स को, इनफैक्ट मेरे ख्याल में एक ही मॉलिक्यूल होगा जो आप बना सकते हैं जो इस स्पेक्ट्रम को सेटिस्फाई करे। तो मैंने ऐसी एग्जांपल चुनी जो बिल्कुल अनएम्बिगुअस हो। एक और एग्जांपल देखते हैं। अभी बुकमिंस्टर फ्लोरीन है, ठीक है, 60 कार्बन एटम्स, ठीक है। आप मास स्पेक्ट्रोस्कोपी के जरिए बता सकते हैं कि 60 कार्बन एटम्स, ठीक है, लेकिन NMR में आपको एक ही पीक नजर आ रही है। You cannot tell the number of carbon atoms. You have to do a reference experiment. But there's only one peak, and this unambiguously determines the symmetry property of Buchmeister field.
All of them are same.
All of them are the same. They are magnetically and chemically equivalent, so you get only one. The carbon 13 spectrum है, याद रखिए। अच्छा, केमिकल शिफ्ट का मैकेनिज्म क्या है, अंडरलाइंग मैकेनिज्म क्या है? अभी एक लंबी चौड़ी बहस शुरू होने वाली है, जिसमें बहुत सी कैलकुलेशन इन्वॉल्व हैं, लेकिन जाहिर है वो कैलकुलेशन नहीं कर सकते इस महदूद वक्त में, और बहुत सी एम्पिरिकल फैक्ट्स भी हैं, बहुत से ऐसे फैक्ट्स हैं जो अभी तक पूरी तरह हमारी समझ में नहीं आए। लेकिन अब देखिए, केमिकल शिफ्ट का एक मैकेनिज्म, एक बिल्कुल ओवरव्यू ये है कि you place your molecule inside an external magnetic field, a static field V naught. Now there is an electron cloud inside the molecule. The electrons are charged. Placing a charge inside, or an electron cloud inside a magnetic field, will cause currents. Suppose you have a toroidal molecule such as benzene ring, an aromatic ring. अब उसके अंदर you have a mesomeric structure or a resonance structure in which the electron cloud is oscillating. Now these electrons are, suppose they are moving in a current fashion, they are making a ring current. Now this oscillating electron cloud produces a field of its own, produces a magnetic field of its own, and if you use the right hand rule, this is the direction of the field that it will produce. ठीक है, coming downwards, upwards, downward, upwards, and there are nuclear spins attached to this electron cloud structure. So they can be in the plane of the ring, they can be inside the ring in the annular region, they can be outside the ring, they can be above and below the plane of the ring. There are different possibilities. Now, depending on the position of the nuclear spin with respect to this electron cloud, the external magnetic field is either enhanced or it is demoted. Lenz's law भी यही कहता है ना कि whenever you have electron current flows in such a way so as to oppose the external magnetic field. ये बिल्कुल classical अगर आप perception use करें, तो the electron cloud or the wave function of the electron, if you are quantum mechanically correct, results in a change in the magnetic field at the site of the nucleus. So this local magnetic field at the site of the nucleus is not the same as the external magnetic field. ठीक है? So if you have no chemical shift mechanism, omega naught is minus gamma B naught. But if you include the effect of chemical shift or the environment of the nucleus inside the molecule, you have to add a correction term, say 1 plus delta. Or you could also write omega naught minus gamma B naught 1 minus sigma. अगर आप देखें कि ये effective magnetic field है, if this is the effective magnetic field the effective magnetic field is now enhanced if delta is positive. In this case, the effective magnetic field is decreased if sigma is positive. So the decrease of the effective magnetic field is like shielding. So this parameter, if it's positive, it could be positive, negative, but this parameter is called the shielding parameter. And this parameter is called the de-shielding parameter. And this is our chemical shift parameter as well. ठीक है? या इसको chemical shift कहते हैं या इसको chemical shift कहते हैं, फर्क नहीं पड़ता. लेकिन ppm स्केल में जो डेल्टा इस्तेमाल हो रहा है वो ये de-shielding parameter है. ठीक है? So the effective magnetic field can either be enhanced or de-emphasized. Now this is a very small parameter. If you take a hydrogen nucleus on its own, you can do a theoretical calculation and see what the chemical shift is. Now if you take hydrogen inside a hydrogen molecule, the diatomic gas, and find out the chemical shift, the hydrogen in the diatomic gas will be shielded because of the presence of a bond, because the presence of an electron cloud, and the shielding will be of the order of 10 to the power minus 6. This parameter is generally of the order of 10 to the power minus 5 or 10 to the power minus 6. ठीक है? तो ये इसका एक आप समझ लें मोटा इसकी डिस्क्रिप्शन है केमिकल शिफ्ट की. अब आगे हम मजीद इसकी थोड़ी सी डिटेल्स में जाते हैं. अब आप ये देखें, अगर ये एक रिंग करंट फ्लो कर रहा है, so in this region which is shown shaded, the magnetic field due to this induced current, this is an induced current, right? This is an induction effect. This induced current is opposing the external magnetic field. So in this region we see shielding. So any nucleus that sticks its head in this region is shielded. But any nucleus or any functional group or any proton that is present in this region outside the annular region of the ring is de-shielded. ठीक है? क्योंकि यहाँ effective magnetic field enhance हो रही है.
So when you are doing an NMR, तो मतलब ये proton, मतलब ये structure obviously एक particular direction में तो नहीं ना मौजूद होगा. It will continue to be going, मतलब changing in its position. So how could you have different shieldings? Like उसमें फिर वो average out होके खत्म नहीं रहता होगा?
ये बहुत अच्छा क्वेश्चन, मैं इसका आंसर मैंने आपके लिए रखा हुआ है. बहुत अच्छा क्वेश्चन है. देखो इस सारी रीजन में डाउनवर्ड पॉइंटिंग फील्ड है, यहाँ भी डाउनवर्ड पॉइंटिंग है, यहाँ भी डाउनवर्ड पॉइंटिंग है, और फील्ड जो एक्सटर्नल है वो अपवर्ड पॉइंटिंग. So the magnetic field in this region is reduced. So it is a shielding effect. ये एक इलेक्ट्रॉन क्लाउड है. फॉर एग्जाम्पल, सिंपल एग्जाम्पल बेंजीन का मॉलिक्यूल है. ये मॉलिक्यूलर ऑर्बिटल है बेंजीन. तो अब देखें, now this is the ppm scale that we have been talking about. This is increasing delta, which means that as you go from right to left, the de-shielding increases. The de-shielding increases. ये बात है, लेकिन delta goes up, the de-shielding parameter is going up. So from right to left, the de-shielding is going up, and from left to right, the shielding is increasing. So more shielded protons occur to the right of the spectrum. अच्छा, ये जो दो टर्म है ना, फ्रीक्वेंसी और मैग्नेटिक फील्ड, ये एक गुजरे हुए बादल के तूफान है. अब जो मॉडर्न एनएमआर में इन चीजों को समझना थोड़ा मुश्किल हो गया है. क्योंकि जो पहले एनएमआर होता था ना, जो स्वीपिंग एनएमआर जिसे कहते हैं, ये कंटिन्यूअस वेव एनएमआर, उसमें ये टर्म्स रेलेवेंट है. अब यूं समझ लें कि जो शील्डेड रीजन में न्यूक्लियस है, जो शील्डेड रीजन में न्यूक्लियस है, अब वो इफेक्टिव फील्ड कम देख रहा है. वो इफेक्टिव फील्ड कम देख रहा है, यानी वो उसकी फ्रीक्वेंसी कम है, ठीक है। उसकी फ्रीक्वेंसी अगर एक मैग्नेटिक फील्ड फिक्स कर दे उसकी फ्रीक्वेंसी कम होगी जो शील्डेड है, या आप यूं समझ लें एक फ्रीक्वेंसी पर उसको रेजोनेट करने के लिए यू नीड अ हायर एक्सटर्नल मैग्नेटिक फील्ड, दैट इज व्हाई द मैग्नेटिक फील्ड इज गोइंग higher in this direction, the frequency is moving higher in this direction. So in old days NMR was done in such a way that the frequency was fixed and the magnetic field was swept. So if you want to resonate this particular proton at a certain frequency, you will have to gradually increase the magnetic field. So that is why this scale, this direction is the direction of increasing swept magnetic field. But both of these terms are reminiscent of the old days of NMR. तो चूँकि हमारी रवायत परस्ती हमें इस बात पर कायल करती है कि हम अपनी रवायतों को ना भूलें, इसलिए ये टर्म्स भी स्ट्रिक्ट इस्तेमाल होती हैं। और आप केमिस्ट्री का लिटरेचर पढ़ें तो इसको अप फील्ड भी कह देते हैं, जो पीक्स राइट पर हैं जहाँ मैग्नेटिक फील्ड हायर है, और इन पीक्स को डाउन फील्ड भी कहते हैं। So more shielded protons are upfield and less shielded protons are downfield. तो आप केमिस्ट्री के लिटरेचर में, आर्टिकल्स में, टेक्स्ट बुक्स में ये टर्म्स इस्तेमाल होती हैं, खास तौर पे ऑर्गेनिक केमिस्ट्री इसको बड़ी सहूलत के साथ इस्तेमाल करते हैं, अपफील्ड और डाउनफील्ड। अच्छा, अब हम थोड़े से मैकेनिज्म्स की बात करते रहे केमिकल शिफ्ट। अब देखिए केमिकल शिफ्ट जो है वो उसके बहुत से कॉन्ट्रीब्यूशंस उसको मिल रहे हैं, ठीक है। अब सिंपल केसेस में कैलकुलेट भी कर सकते हैं कलम दवात के साथ और कागज के साथ, मैथमेटिका के साथ, ठीक है। सिंपल केसेस में आप एब इनिशियो कैलकुलेशन भी कर सकते हैं केमिकल शिफ्ट को डिटरमिन करने की। लेकिन इसके बहुत से फैक्टर्स हैं, एक है डायमैग्नेटिक फैक्टर, एक है पैरामैग्नेटिक फैक्टर, एक है अब एक प्रोटॉन, ठीक है, it's a part of a bond. A proton is bonded to something such as a carbon. So there is a molecular orbital or a wave function, an electronic wave function in the vicinity of the proton. So this is called a local effect. But the molecule as a whole has a certain bond structure. It has a certain molecular orbital structure. So the whole molecule can affect one particular proton. So there are remote effects as well, and there are other effects as well. So let's talk about the easiest one of them, the local diamagnetic effect. Now suppose you have methyl halides. Methyl halides. You have iodomethane, bromomethane, chloromethane, fluoromethane. Okay. अब सिंपल स्केल पे पॉलिंग इलेक्ट्रोनेगेटिविटी को Fluorine is the most electronegative element. Fluorine pulls the electron away from the carbon and hence away from the protons. Now when the electrons are pulled away from the protons, the shielding effect will decrease. So you look at the overlap of the electronic wave function at the site of the nucleus. If electrons are pulled away from the nucleus, the proton will be less shielded or more de-shielded. Agreed?
Yes, sir.
ठीक है ना? तो जो इलेक्ट्रोनेगेटिविटी बढ़ रही है, आप देखें ये de-shielding बढ़ रहा है, ठीक है। और इसी स्केल पर अगर मीथेन देखें, CH3H को देखें, तो वो 0.1 की वो उससे भी कम, ठीक है। तो ये एक सिंपलेस्ट मैकेनिज्म है जो मैं सोच सकता था समझाने के लिए कह रहे थे कि now you have an element which is electronegative, it's pulling electrons away from the site of the nucleus. That is, it is decreasing the overlap of the wave function at the site of the nucleus. In other words, this term is decreasing. Say the 1s orbital at the site of the nucleus, this term is decreasing. The overlap of the wave function at the proton is decreasing because electrons are being pulled away from the proton. Okay. Hence, the shielding effect decreases or the de-shielding goes up. एग्जांपल देखते हैं उसी की एक्सटेंशन। अब ये प्रोपेन है, प्रोपेन में दो तरह के प्रोटॉन्स हैं, दो मैथिलीन ग्रुप्स हैं और एक मिथाइल, ठीक है, CH3 CH2 सॉरी दो मैथिल ग्रुप्स हैं CH3 CH2 CH3, ठीक है, और एक मैथिलीन ग्रुप है। अब प्रोपेन का अगर आप स्पेक्ट्रम देखें तो उसमें एक पीक यहाँ है, एक पीक यहाँ है, दिस कॉरेस्पॉन्ड्स टू द मेथिल प्रोटॉन, दिस कॉरेस्पॉन्ड्स टू द मैथिलीन प्रोटॉन्स। अब अगर देखें ये वाला कंपाउंड देखें, यानी 1 क्लोरोब्यूटेन, ठीक है, 1 क्लोरोब्यूटेन। अब ये वाले जो प्रोटॉन्स हैं
सबसे अलग
दे आर गोइंग डाउन, ठीक है, मोर डी-शीटिंग because they are present next to an electronegative chlorine atom which is pulling electrons away from these protons. Therefore the shielding decreases or the de-shielding goes up, ठीक है। तो ये वाला प्रोटॉन यहाँ पे है, अच्छा ये CH2 प्रोटॉन यहाँ पे है। अब ये जो CH2 प्रोटॉन्स हैं, why are they going downfield or why is the de-shielding more in these protons as compared to the protons in the methylene groups in propane? Because this chloride atom has a remote effect as well. The range of this electronegative atom is not just confined to 2 bond lengths. कितनी bonds हैं क्लोरीन और हाइड्रोजन में? 2 bond lengths हैं, और इस क्लोरीन और हाइड्रोजन में 4 bond lengths हैं, 4 bond lengths हैं। तो इस इलेक्ट्रोनेगेटिव एलिमेंट के डी-शील्डिंग पे 4 बॉन्ड लेंथ्स तक एक्सटेंड हुआ है, ठीक है, इनफैक्ट 6 बॉन्ड लेंथ्स तक एक्सटेंड हुआ है, क्योंकि ये जो पीक है CH2 की, इसका जो टेम्परेचर है वो स्लाइटली हायर है डी-शील्डिंग एज कंपेयर्ड टू दी कॉरस्पॉन्डिंग पीक इन प्रोपेन, लेकिन मेथिल ग्रुप तक उसका इफेक्ट बिल्कुल खत्म हो जाता है। तो इसलिए ये दोनों पीक्स एक ही ppm रेंज में। तो एक रिमोट इफेक्ट है। डायमैग्नेटिज्म का मतलब ये है कि when you apply an external field, that when you apply an external field, a current flows so that it opposes the external field, which means de-shielding. So there is a remote diamagnetic effect as well, and there is a range of this electronegativity phenomenon. अब आपको मैकेनिज्म समझ आ रहे हैं कि केमिकल शिफ्ट किस तरह इंड्यूस होता है। बिल्कुल इसी तरह हम एग्जांपल देख सकते हैं नाइट्रोइथेन, ठीक है, अच्छा अब ये
पॉजिटिव का स्पेक्ट्रम है,
सॉरी
ये प्रोटॉन
ये प्रोटॉन स्पेक्ट्रम
3 क्यों आ गए?
इनफैक्ट ये नाइट्रोप्रोपेन मैंने ना एक
बिकॉज़ ऊपर नाइट्रोप्रोपेन
मैंने एक CH2 का बनाया, सॉरी ये यहाँ एक और CH2, ठीक है, और जाहिर है जो अल्फा प्रोटॉन्स हैं जो नाइट्रो ग्रुप के बिल्कुल साथ में, दे विल बी मोर डी-शील्ड। अच्छा, अब सब्स्टिट्यूटेड बेंजीन्स की देखें बात, बहुत इंटरेस्टिंग एग्जांपल है। अच्छा, हमें ये पता है कि बेंजीन इज ऑलमोस्ट एट अबाउट 7.2 ppm प्योर बेंजीन, ठीक है, एक तरह के प्रोटॉन। अब हमारे पास इलेक्ट्रॉन विड्रॉइंग ग्रुप्स भी हो सकते हैं, इलेक्ट्रॉन डोनेटिंग ग्रुप्स भी हो सकते हैं। अब let's look at the nitro group, which is electron withdrawing.
Yes, sir.
Okay. So, or we can have the nitrile group or any electron withdrawing group. अभी नाइट्रोबेंजीन है, ठीक है, अब ये इसके रेजोनेंस स्ट्रक्चर है। अच्छा, अब नाइट्रोबेंजीन का एक रेजोनेंस स्ट्रक्चर ये है कि जिसपे ऑर्थो पोजीशन पे ये चार्ज है, और एक रेजोनेंस स्ट्रक्चर ये है जिसपे पैरा पोजीशन पे चार्ज है। अब ortho or para nitrobenzenes are shifted, they go more de-shielded, okay? They are shifted downfield, they go to the left. Because of the electron withdrawing properties of the nitro group, the electron density is decreased at this position, and the electron density is also decreased at this position. And the effect is stronger for the ortho group because it is close to the electron withdrawing group. So the ortho resonance structure of nitrobenzene. So you get a peak from the ortho resonance structure and a peak from the para resonance structure. both of these peaks go upfield with respect to benzene. ठीक है? और मेटा स्ट्रक्चर में भी also goes downfield. Sorry, it is more de-shielded. Likewise, if you have electron donating groups, for example, you have phenol or you have phenylamine, ठीक है? You get the opposite effect. You increase the shielding because now the lone electrons are injected into the aromatic ring, and the electron density at the ortho and the para sites goes up. So you get a higher shielding effect, and so the peaks are shifted towards the right of the spectrum. You go upfield with respect to benzene. ठीक है? अच्छा, अभी लोकल पैरामैग्नेटिक इफेक्ट्स हैं. अब मैं सोच रहा हूँ मैं आपको बताऊँ क्या ना.
सर जो आपने इसे पिछले वाले इफेक्ट्स बताए इनका नाम बता दें. इसे पिछले
ये सारे के सारे डायमैग्नेटिक इफेक्ट्स हैं, लोकल और रिमोट. ठीक है, क्योंकि हम रिमोटनेस भी देखते हैं. वी लुक एट द रेंज ऑफ द डायमैग्नेटिक इफेक्ट. ये कितने बॉन्ड लेंथ तक आप जा सकते हैं. ठीक है, वो इफेक्ट यकीनन रिड्यूस हो रहा है स्ट्रेंथ में, लेकिन मौजूद जरूर है. अच्छा, अब देखिए, अब एक मॉलिक्यूल में एक प्रोटॉन है. देखिए, मॉलिक्यूल के अंदर इलेक्ट्रॉन पूरा एक मॉलिक्यूलर स्ट्रक्चर है और वो बॉन्ड्स पूरे मॉलिक्यूल में फैले हुए, सरायत किए हुए. अब जब हम मैग्नेटिक फील्ड में मॉलिक्यूल को रखते हैं, जरूरी नहीं है कि उस पर्टिकुलर प्रोटॉन के साथ जो बॉन्ड है वो अपना किरदार अदा कर रहा है. द मॉलिक्यूल एज अ होल हैज एन इलेक्ट्रॉन क्लाउड, has a bonding structure, has an orbital structure. Agree? So when you place that molecule inside a magnetic field, it develops a dipole moment. For example, suppose this is a molecule. This is a schematic representation of a molecule in which this is a proton whose NMR we are doing, and this is some X, something else, the rest of the molecule. For example, it could be the triple bond in acetylene. Suppose you have fluoroacetylene. Or let's not say fluoro. All right, fluoro is fine. Fluoroacetylene. Now this H is this particular species, and the rest of the molecule is represented by this ellipse. This is a triple bond as well, and all. So this is the rest of the molecule. Now there is an electron cloud associated with the rest of the molecule. You place this molecule inside a magnetic field. Now there is a distance between, there is a bond length or a distance between this nucleus and the rest of the molecule. Let's call it R. And this is a preferred axis of the rest of the molecule. Okay? Suppose the long axis of the ellipse represents the preferred axis. For example, in this case, it's just the axis of this molecule. This is an axial molecule. Alright. Now there is a certain angle between the ellipse, the long major axis of the ellipse, and the bond vector. ठीक है? अब एक्सटर्नल मैग्नेटिक फील्ड में जब आप रखते हैं मॉलिक्यूल को, तो बिकॉज ऑफ द इलेक्ट्रॉन क्लाउड इट डेवलप्स अ मैग्नेटिक मोमेंट. Now what is the magnetic moment? The magnetic moment depends upon the applied external field. Okay? And what is the proportionality constant? The proportionality constant between magnetization and the applied field is called the susceptibility. ठीक है? Chi. Agreed? आपने electromagnetism में पढ़ा होगा. अब देखो, susceptibility anisotropic है. अगर आप external magnetic field parallel to the ellipse apply करें, you have one susceptibility, chi parallel, and if you apply the magnetic field perpendicular to the preferred axis, you have another susceptibility. Just imagine that in this molecule you are applying a field parallel to the axis and perpendicular to the axis. Different magnetic moments will develop. Because chi parallel is not the same as chi perpendicular. Now let's look at this example. You have a magnetic field. वो ये आपके सवाल का भी जवाब है कि tumbling हो रही है. You have a magnetic field. And this is the orientation of the molecule. Now, the magnetic field, the ellipse is perpendicular to the field. So, a magnetization is developed, and that magnetization will be given by chi perpendicular. And that dipole moment will affect, it will generate a magnetic field. This starts behaving like a magnet, a dipole, ठीक है? और उसकी magnetic field इस तरह होगी, और वो magnetic field इस proton को affect कर रही है. तो ये एक effective magnetic field देख रहा है, which is the vector sum of the external field and the field due to this dipole. So this is called a dipolar field. ठीक है? अब this dipolar field depends upon the distance r. In fact, depends on 1 over r cube. डिस्टेंस बढ़ा दोगे ये डाइपोलर फील्ड जो ये प्रोटॉन दिख रहा है वो r क्यूब के इनवर्सली प्रोपोर्शनल है. ठीक है? अच्छा, इस पर्टिकुलर कॉन्फ़िगरेशन में देखें, the ellipse is now parallel to the, suppose the molecule has rotated, the ellipse is now parallel to the magnetic field. So the magnetic dipole moment that is created in this case is different from this case, because the operative susceptibility, the principal susceptibility, is now parallel to the applied field. So a different dipole is created, a different dipole moment is created. So the field seen by this proton is now different. Okay? And it is, in this case, you will graphically observe that the field, the induced field or dipolar field, is aiding the external field. And in this case, the dipolar field is decreasing the external field. So this is a shielding effect, and this is a de-shielding effect. Okay. Now it turns out that the naive way of thinking is that since we have motional averaging, the shielding and the de-shielding cancels out. Okay, this is the naive expression. But in effect, if you work out the mathematics for the field due to a dipole, there is a term that is 3 proportional to 3 cosine squared theta minus 1. And you have to take the average of this term, which means you have to take 3 cosine squared theta minus 1, multiply it with sine theta d theta and integrate from 0 to pi. And you also have to integrate with respect to d phi, where phi is from 0 to 2 pi. Now the average of this term is not 0 for all values of theta. Therefore the dipolar field does not cancel out. Do you remember integrals of this kind from the modern physics class? Sine theta comes from it's a metric that allows you to do integration over this polar coordinates. Okay? So this term is not 0. The average of this term is not 0. So even though there is motional averaging, and in one particular configuration you have shielding and in the other you have de-shielding, but if you take the average it comes out to be a finite value unless theta is fixed. ठीक है? तो जब थीटा एवरेज हो रहा है तो ये इफेक्ट्स कैंसिल आउट नहीं होते. हाँ अगर थीटा फिक्स्ड है, अब देखो ये टर्म देखो 3 कोसाइन स्क्वायर थीटा माइनस 1, और मैं आपको एक इंटरेस्टिंग चीज दिखाऊं, ये देखो अगर 3 कोसाइन स्क्वायर थीटा माइनस 1, अगर ये चीज एवरेज जीरो उसी वक्त होगी जब when this thing is equal to 0 and you solve this polynomial, make it equal to 0, you get theta equal to 54.74 degrees, which is the magic angle, which is the same angle that you come across in tetrahedral symmetry. In tetramethylsilane or methane, the bond angles are 54.74 degrees.
109.7 होते हैं ना, तो वाइस
हाँ उसका हाफ कर
हाफ,
ठीक है. So this is the tetrahedral angle. All right. So giving you one particular example, this is the rest of the molecule in a cone that is within an angle of 54.74 degrees. You have say shielding, and outside you have de-shielding. Here it depends upon the relative strengths of the parallel and the perpendicular susceptibilities. The effect reverses, but whatever the case is, within a particular region you have shielding, and in the other region you have de-shielding. So if this is the molecule, if your proton of interest lies here, you will have shielding. If your proton of interest lies here, you will have de-shielding. So this tells us that there is a lot of dependence on the geometry of the molecule, on the chemical shape, where that particular species is lying inside the molecule. What is the stereochemistry of the molecule? Now let me give you some examples. अच्छा, ये चीज आपको यहाँ भी एक बहरूपी अंदाज में नजर आ रही है. ये देखें, ये जो मैंने बनाया है, ये जो रीजन बना हुआ, मैंने तो नहीं बनाया, मैंने कहीं से फिगर ली है. ये जो रीजन बना हुआ, ये जो एंगल है ना कोन्स का, ये बता this region, this interface is the interface between the shielding and the de-shielding, और ये एंगल 54.74 डिग्री. जाहिर है ये एंगल ट्वाइस है इसके, लेकिन इस एक्सिस से इस होराइजन का एंगल 54.74. तो इस रीजन में शील्डिंग है, उसके बाहर de-shielding. तो ये जो एंगल है ना 54.74, ये बड़ा मैजिक एंगल, ये बहुत अहमियत का हमें है NMR. सॉलिड्स का जब NMR करना हो ना, तो आप सॉलिड को 54.74 डिग्री के एंगल पे रखते हैं मैग्नेटिक फील्ड से, उसको रैपिडली स्पिन करते हैं, तब सॉलिड का NMR becomes comprehensible. It's called magic angle spinning. So it's a very complicated but a beautiful effect. So this is the Legendre polynomial, ठीक है. और ये दरअसल d ऑर्बिटल की भी यही फॉर्म है, 3 कोसाइन स्क्वायर थीटा माइनस 1 टर्म. उसमें भी आप देखें नोडल प्लेन बनते हैं, जहाँ पे ऑर्बिटल, जहाँ पे वेव फंक्शन 0 हो जाता है, बनते हैं वो भी 3 कोसाइन स्क्वायर थीटा माइनस 1 एक्सप्रेशन है d ऑर्बिटल की. या यूं कह लें, दिस इज द y2 स्फेरिकल हार्मोनिक. So there are dipolar effects as well. So dipolar effects example, a chemical shift is being influenced by neighboring species inside the molecule, not just the bond which connects the proton to a carbon. It's also affected by neighboring bonds. For example, we have the examples of the alkanes, the alkynes, and the alkene, right? Ethylene, acetylene, ethane. अच्छा, अब देखिए अगर आप sp2, sp3 और sp hybridization की बात करें, this has the largest s character, ठीक है? This is sp hybridized, this is sp2 hybridized, this is sp3 hybridized, ठीक है? So you expect the bond, the molecule which has the largest s character to have the largest overlap of the wave function at the nucleus. So you expect the C2H2 to lie here, somewhere here. But you do not, the NMR spectrum is not borne out by this deduction or by this conjecture because of the dipolar effects. Because this is a triple bond, this is a double bond, And because of the dipolar effects, which are a bit complicated to explain here, the chemical shift is heavily influenced by the kind of bond. So, and this is not the bond between the proton and the carbon, it's a bond that is present inside the molecule, some other bond.
Sir, if there were no chemical shift in which the neighboring bonds are affecting the NMR spectrum, then the C2H2 should be towards the left?
Right, it should be more D-shaped. Because it has the highest S character. If you just look at the local diamagnetic effects, the S character of this particular molecule is more, it's 50%. Therefore, the overlap of the wave function along this axis will be higher. So this proton will be seeing the more, will be seeing
more D-shaped.
It will be more D-shaped.
Because more electrons are on H. So when
No.
it's sp3 hybridized.
Okay, when it is sp hybridized,
Yes, sir.
so you have two carbons. So the sp hybridization is between the two carbons, right?
Yes, sir.
Or it's between the carbon and the hydrogen. So there's an S bond, a linear molecular orbital, right? It's a linear combination of atomic orbitals. You have an S bond, all right? If you have an sp3,
So actually this is the CC bond and the CH bond are actually SP bonds total. तो you cannot like हम उसको हम S या P हम नहीं क्योंकि वो तो hybridized होकर
SP bond है. And sp bond is more between the nucleuses.
it's more closer to the nucleus.
Yeah.
all right? So it's
Yeah.
so the overlap of the sp bond with
So
the
for example,
proton.
in the S, sir, if
sp bond का overlap proton पे ज़्यादा होगा ना?
Sir, what I want to say is that when the sp3 hybridization होती है, so the electrons are relatively far from the
Further
nucleus.
apart.
Yeah, but if is sp hybridization, then they are relatively closer to the nucleus, whatever nucleus it is, whether it is carbon nucleus or hydrogen nucleus. So since
I guess the SP जो closer तो होगा न्यूक्लियस के, लेकिन वो कार्बन के न्यूक्लियस से ज़्यादा क्लोज होगा क्योंकि जो हाइड्रोजन का न्यूक्लियस है ना वो तो S है ना, वो तो S ही है ना, 1S है वो. लेकिन तो इसका मतलब है कि वो चुके SP की
कार्बन पे हाइब्रिडाइजेशन है.
कार्बन में हाइब्रिडाइजेशन है, तो कार्बन का ज़्यादा होगा, हाइड्रोजन से कम नहीं होगा. तो इसलिए डी-शेडिंग, क्योंकि हमारे प्रोटॉन के लिए देखना है तो प्रोटॉन पे डी-शेडिंग
ये कार्बन पे हाइब्रिडाइजेशन है. sp और sp2 sp3 एटॉमिक ऑर्बिटल है.
yes, sir.
तो कार्बन पे ओवरलैप ज्यादा होगा इलेक्ट्रॉनिक वेव फंक्शन का. अच्छा, एक और एग्जांपल देखते हैं. अब ये कौन सा मॉलिक्यूल है?
So phenanthrene.
फिनांथ्रीन.
Yes, sir.
अब ये फिनांथ्रीन पे ये जो प्रोटॉन है, अब ये एक एरोमेटिक स्ट्रक्चर है, ठीक है? अब इस प्रोटॉन की केमिकल शिफ्ट 8.6 ppm है. It's more de-shielded than a normal benzene proton. Now, if this phenanthrene is substituted by an alkyne group here, now this proton is in the vicinity of a triple bond. Therefore, it is affected by the dipolar field. And this is a non-local effect. So this shifts the chemical shift downfield by about 2 ppm.
अब ये कैसे शो हो सकते हैं कि वो जो H का ट्रिपल बॉन्ड की विसिनिटी है वहाँ से इफेक्ट हो रहा है या थ्रू द मॉलिक्यूल हो रहा है? because उसको तो डिलोकलाइज इलेक्ट्रॉन्स हैं हर एक.
अच्छा, ये इलेक्ट्रॉन विड्रॉइंग या इलेक्ट्रॉन इसकी है
इलेक्ट्रॉन विड्रॉइंग है वैसे.
इलेक्ट्रॉन, ये दोनों इफेक्ट्स कंबाइन हो गए. ये दोनों इफेक्ट्स कंबाइन हो गए.
सर बेसिकली हम कुछ कह नहीं सकते क्योंकि ये बिकॉज इट्स अ कार्बन, सो नॉर्मली जो इलेक्ट्रॉन विड्रॉ या दे रहे होते हैं दे आर हेटेरो एटम्स. तो
आप कुछ कह नहीं ना सकते. इस केस में फिर ये डाइपोलर फील्ड ज्यादा इफेक्ट हो रहा है.
लेकिन सर डाइपोलर फील्ड ठीक है.
और फिर आप दूसरी बात ये कि आपको उस डाइपोलर फील्ड की एग्जैक्ट एक्सप्रेशन पता है. It has a 1/r cube dependence. If you substitute the alkyne at different points, you can do a more careful synthesis. You substitute the alkyne at different points, take an NMR spectrum, you will get different chemical shifts, and you can correlate those chemical shifts with the structure that you made. Okay, so it's not a one-shot process. You have to do multiple kinds of experiments, multiple kinds of synthesis to be confident of what you are how you are explaining the effect. अच्छा, ये रिंग करंट्स की मैंने बात कर दी आपको कि आप देखें इस प्लेन में और तरह के इफेक्ट्स हैं, प्लेन के ऊपर और नीचे और तरह के इफेक्ट्स हैं, और विद इन द रिंग और तरह के, विद इन द रिंग आप देखें शील्डिंग इफेक्ट है, आउट बियॉन्ड द रिंग डी शील्डिंग इफेक्ट है, above and below the plane डी शील्डिंग इफेक्ट है, ठीक है. सो इट डिपेंड्स अपॉन व्हिच प्रोटॉन यू टॉकिंग अबाउट, whether it is inside the ring or outside the ring, depends a lot on the stereochemistry. Some examples. So you have this cyclo, now what is this? One cyclohexa 1,3-diene.
Yes.
Cyclohexa 1,3-diene. अच्छा, this is benzene 7.3 ppm पर, और आप ये देखें ये जो दो प्रोटॉन्स हैं ये 5.9 ppm पे, they are more shielded. Now if you go back,
So I think उसमें ये है कि the benzene is totally a planar molecule.
और दूसरी और ये एक resonance
It's not,
structure,
but it is planar. The hydrogens are planar.
लेकिन ये resonance structure नहीं है ना, ये resonance structure नहीं, इसमें रिंग करंट फ्लो कर रहा है, इसमें रिंग करंट फ्लो नहीं कर रहा. हाँ, ये डीलोकलाइज्ड इलेक्ट्रॉन्स हैं, ये लोकलाइज्ड इलेक्ट्रॉन्स हैं. अब उस डीलोकलाइजेशन की वजह से एक रिंग करंट फ्लो हो रहा है. यू कैन सी दिस रिंग करंट इफेक्ट हियर. यू हैव प्रोटॉन्स हियर इन द बेंजीन, ठीक है, दे आर आउटसाइड द एनुलर रीजन एंड दे आर इन द प्लेन ऑफ द बेंजीन. नाउ हियर you have a de-shielding effect, and this de-shielding is evident. This proton is more de-shielded than these protons. So you can see a ring current here, but you don't have a ring current here.
We don't have a ring current, but we definitely have some conjugation.
Of course, but here you have complete conjugation. Now let's look at this example. This is a dimethyl substitute pyrene. If you look at this structure, these methyl groups are above and below the plane of the aromatic structure, the plane of the aromatic molecule. The normal protons that are inside the plane have a certain de-shielding, but the methyl protons that are above and below the ring, that are above and below the planar structure of this aromatic molecule, they are heavily shielded. Heavily shielded. You can refer back to the protons that are above and below, they are heavily shielded. So this is a complicated molecule, new kind of lot of research is going on these kinds of molecules, and these molecules are called annulenes. This is 18 annuline because there are 18 carbon atoms, and this is an aromatic compound as well because it follows the aromaticity rule, 4n plus 1 or 4n plus 2 if n is equal. ठीक है. अच्छा, अब ये जो दो प्रोटॉन हैं, ये प्रोटॉन और ये प्रोटॉन, this is outside the ring, this is inside the ring. Something that is inside the ring is heavily shielded. So you get two kinds of protons, you get two peaks from this molecule. ठीक है, so it all beautifully knits up together. अच्छा, हाइड्रोजन बॉन्डिंग का बड़ा अहम रोल है. हाइड्रोजन बॉन्डिंग की जो एग्जैक्ट मैकेनिज्म है ना, अभी जो अगर आप लिक्विड एथेनॉल ले लें, यानी हाई कॉन्सेंट्रेशन का एथेनॉल है,
So it is 1 molar in water.
this is not in water, this is in
So is it 1 molar in a
this
protein or protein?
This is in, I think, carbon tetrafluoride, because we don't want hydrogen bonding. This is an extreme case of no hydrogen bonding. This is hydrogen bonding. This is in water.
Is it soluble in carbon tetrachloride?
think so.
So carbon tetrachloride is a
non-polar.
Yes, sir. It shouldn't be.
I think his point is that
It's liquid. You can take liquid, right?
So basically,
You can take an NMR spectrum at minus
I think, for
25
example,
degrees
if you
centigrade.
dissolve it in water, then the NMR spectrum will be definitely different because the hydrogen bonding in water will be different.
So take liquid ethanol, or freeze it, or take the temperature to be minus 25 degrees centigrade. The point is that we want ethanol with no hydrogen bonding.
So it would still have hydrogen bonding, but
So it
compared
would
to those
always
lower
have
solution, definitely
hydrogen
it would
bonding.
have lesser one. So that is okay.
Okay, so the point of this slide is to show that hydrogen bonding does have an effect on the resonance of the hydroxyl ion. ठीक है, अभी जो hydroxyl ion में जो प्रोटॉन है ये हाइड्रोजन बॉन्ड होगा ना। अब जो आप इसको डाइल्यूट किए जा रहे हैं, आप हाइड्रोजन बॉन्डिंग को बढ़ा रहे हैं।
So if it is in water, then you increase.
बाकी चीजें वाटर में, ये अगर वाटर में नहीं आप कर सकते तो आप लिक्विड ले लें।
फिर वो मोलैरिटी नहीं ना आप कह सकते, वन मोलैरिटी।
तो इसलिए मैं कह रहा हूँ कार्बन टेट्राक्लोराइड में ले लें। It's immiscible, but still you can talk about molarity. Correct? If you don't go by the definition of molarity, it's dissolved. Take something that is in a relatively pure form or in the liquid form. देखिए जो प्रोटॉन जो रेजोनेंसेस हैं हाइड्रोक्सिल ग्रुप पे, they are rapidly changing with molarity or with the hydrogen bonding. So hydrogen bonding has a very pronounced effect on the chemical chain. ये एग्जांपल है एक इंटरमॉलिक्यूलर हाइड्रोजन बॉन्डिंग।
अच्छा, हाइड्रोजन बॉन्डिंग में शील्डिंग बढ़ रही है।
हाइड्रोजन बॉन्डिंग में शील्डिंग कम हो गई।
शील्डिंग बढ़ रही है। अब इसका मैकेनिज्म जो है ना, अच्छा मेरे पास एक स्लाइड थी इंट्रामॉलिक्यूलर हाइड्रोजन बॉन्डिंग की, लेकिन वो मैं डालना भूल गया हूँ। अच्छा, इसका जो रीजन है ना हाइड्रोजन बॉन्डिंग केमिकल शिफ्ट को किस तरह इफेक्ट कर रहा है, इट्स अनक्लियर एट द मोमेंट, वी डोंट नो। ये मुमकिन है कि जो ऑक्सीजन है वाटर का, जब हाइड्रोजन बॉन्ड बन रहा है या कोई भी वैन डर वाल्स इंटरेक्शन हो, तो ऑक्सीजन एक इलेक्ट्रिक फील्ड अप्लाई कर रहा है इसके इलेक्ट्रॉन क्लाउड पर, और उस इलेक्ट्रिक फील्ड की वजह से the electron density on the proton changes, which causes a change in the shielding condition. So we are not very sure about the mechanism of the dependence of the chemical shift on the hydrogen bonding, but the effect is experimentally there. Now this is all that I have. Okay, and one of the most important effects that we should be aware of is that if you have a paramagnetic ion like iron 2+, or cobalt 3+, cobalt 2+, or chromium, one of the rare earth metals or the transition metal ions, paramagnetic, which has a magnetic moment, it makes the peaks go upfield. It shields the protons, heavily shields the protons. So this is an example of a porphyrin complex. ठीक है? Porphyrin complex की बहुत अहमियत है ना, ये सुनने में आया। अब देखिए, अगर ये जो मेटल है, जिंक है, which is diamagnetic, does not have a pronounced magnetic moment. The peaks are in the positive part of the ppm scale. And if you replace the zinc with paramagnetic iron, an iron peaks are shielded, strongly shielded. So whenever you do organometallic chemistry, if in the Wilkinson catalyst you replace the phosphine ligand, the triphosphine ligand with a hydrogen, and take the spectrum of hydrogen with it directly bonded to a metal such as ruthenium or rhodium, the peaks will be really high, upfield.
So on the right side.
On the right side.
Very shielded.
बिल्कुल। अच्छा, आपके पास हिम्मत है 10 मिनट?
सर बिल्कुल है।
अच्छा, अब मैं थोड़ी सी बात करना चाह रहा हूँ, पैरा हाइड्रोजन इंट्रोड्यूस करना चाह रहा हूँ। स्पेक्ट्रोस, आपने पैरा हाइड्रोजन के बारे में पढ़ा है? स्पेक्ट्रोस्कोपी के कोर्स में पैरा हाइड्रोजन का तज़किरा बड़ा अहम है।
नाम सुने जेन से निकल गए क्या पैरा हाइड्रोजन।
अच्छा देखो, NMR की एक प्रॉब्लम तो ये है ना कि इट्स एन इनसेंसिटिव टेक्निक, क्योंकि अगर ये दो एनर्जी लेवल्स हैं, इन दोनों के दरमियान पॉपुलेशन डिफरेंस इज वेरी स्मॉल, ठीक है, क्योंकि इनका स्पेसिंग बहुत कम है। तो इफ यू वांट टू इंक्रीज द सेंसिटिविटी, यू हैव टू गो टू नॉन बोल्ट्जमैन डिस्ट्रीब्यूशंस, नॉन थर्मल स्टार्टिंग स्टेट्स। दैट इज, यू वांट to have a very large population difference. So there are different ways of achieving this. Right, let's talk, before we go into parahydrogen, another example of very large chemical shift, which is actually very useful from a technological perspective. Xenon. Xenon 129, a very large molecule. It's a noble gas. So, for noble gases, their closed shell, only the diamagnetic effects are important. अब xenon इतना बड़ा मॉलिक्यूल है, हाइड्रोजन के लिए केमिकल शिफ्ट बहुत थोड़े होते हैं, 5, 10, 15 ppm बस. लेकिन जितना बड़ा मॉलिक्यूल आप ले लें, जितना बड़ा उसका इलेक्ट्रॉन क्लाउड है, फ्लोरीन ले लें, कार्बन 13 हद तक ले लें, xenon ले लें, फॉस्फोरस ले लें, उसमें केमिकल शिफ्ट डिस्पर्शन बहुत ज्यादा होता है. क्योंकि इलेक्ट्रॉन क्लाउड इतना बड़ा है, the effect of shielding and de-shielding is very pronounced. मैं एग्जांपल देता हूँ, xenon बहुत बड़ा एक एटम है. अब xenon को एनरिच करते हैं आप उसका NMR कर सकते हैं या आप हाइपर पोलराइज कर सकते हैं xenon. उसके मुख्तलिफ तरीके हैं, हम डिटेल्स में नहीं जा सकते. लेकिन अगर xenon गैस है ना, उसकी केमिकल शिफ्ट है 0 ppm, लेट्स से. अब उस xenon को आप पानी के अंदर डिसॉल्व कर दें, उस xenon को पानी के अंदर डिसॉल्व कर दें, 200 ppm का शिफ्ट आ रहा है. यानी just placing xenon in a different solvent changes the chemical shift. So the chemical shift is not only influenced by other species inside the molecule, inside the same molecule, it is also influenced by other molecules, by the solvent molecules. And the reason is the dipolar field, because the dipolar field is just a magnetic field through space. Dipolar field यही है ना कि एक molecule का एक हिस्सा acts as a dipole, acts as a magnet, and it produces a magnetic field at a certain distance. Now the field, the dipole need not be in the same molecule. It can be in a neighboring molecule. It can be in the solvent. So the dipolar coupling is through space coupling. Is through space coupling. It's just like placing two magnets close by. जो अगले लेक्चर में हम कपलिंग देखेंगे वो थ्रू स्पेस नहीं, वो थ्रू बॉन्ड कपलिंग है. बट डाइपोलर कपलिंग इज थ्रू स्पेस कपलिंग. अब xenon को पानी में डिसॉल्व करें, ब्लड में डिसॉल्व करें या DMSO में डिसॉल्व करें, there's a huge range of chemical shifts that can be achieved. इस xenon को आप एक केज में बंद कर दें, क्रिप्टोफेन केज में बंद कर लें, you get a different chemical shift. अब इसके बहुत से फायदे हैं. आप हाइपरपोलराइजेशन की वजह से देखो, गैस का NMR करना बहुत मुश्किल है. क्या वजह? हमने बहुत काम देखे होंगे गैस NMR स्पेक्ट्रल. क्या वजह गैस का NMR करने का मुश्किल क्यों है? उसकी बोलो बोलो
उसका सैंपल लेना थोड़ा
कंसंट्रेशन.
टेस्ट ट्यूब में आप गैस भर लें, कंसंट्रेशन, डेंसिटी, लिक्विड और सॉल्यूशन की निस्बत तो गैस orders of magnitude less dense है. The number of spins that are contributing to the signal is very small. One reason. Second, gas molecules relax very fast. The spins in the gas molecule relax very fast because the gas molecules are seeing the walls of the test tube because of the collision, and they are colliding with one another. So the relaxation is fast. The P's are very small. So it's very difficult to do low pressure NMR. It's easy to do high pressure NMR, but for high pressure NMR you really have to go to very high pressure, and you have to make a cell that can hold a gas to high pressure, and you don't want to make a metal cell because you don't want to put a metal inside the NMR spectrometer. So gas NMR is really very difficult. तो फिर आप lungs का, lung के अंदर MRI अगर करना है, lung के अंदर जो void spaces हैं वहाँ तो गैस ही आप पाएंगे, तो उसमें आपको गैस को hyperpolarize करना पड़ेगा. So xenon can be hyperpolarized, and you can inhale xenon, and when you inhale xenon, आप अपना सांस रोकें और फिर MRI करें और फिर वो सांस बाहर निकालें. You can do lung MRI with hyperpolarized xenon. जी.
So hyperpolarization का मतलब क्या है?
Hyperpolarization का मतलब ये है, देखो Boltzmann distribution है ना, जो कहता है कि population difference between the two levels is very small at room temperature. Now you have to increase the population difference. More and more spins have to be in one state. You have to make a pure quantum state, in other words. That is called hyperpolarization. अब मतलब ये एग्जांपल्स हैं. अब ये xenon फ्री xenon है जो वाटर के अंदर डिसॉल्व है, उसकी और xenon को एक केज में बंद कर दें. ट्रिप्टोफैन केज में उसकी एक डिफरेंट केमिकल शिफ्ट. xenon की केमिकल शिफ्ट इज सरफेस डिपेंडेंट, रियली सरफेस डिपेंडेंट. अब रबड़ पर और उसकी शिफ्ट होगी, वुड में और शिफ्ट होगी, ब्लड में और शिफ्ट होगी, बिकॉज ऑफ द लार्ज इलेक्ट्रॉनिक क्लाउड. अब इससे आप बायोसेंसर्स बना सकते हैं कि अगर ये आपके पास केज है, उसके अंदर xenon एटम है, एक लिंकर मॉलिक्यूल है, एक प्रोटीन है, ठीक है, एक लिगेंड है और टारगेट है. तो जब ये टारगेट इसके साथ आके लैच होगा, केमिकल शिफ्ट ऑफ द xenon विल चेंज. सो यू कैन यूज इट एज अ बायोसेंसर. लोग इस्तेमाल करते हैं. अब बस ये प्योर xenon गैस है, ये xenon dissolved in water और बायोसेंसर का सिग्नल है when you have found the particular antibody to which your ligand attaches. So you can do all kinds of cancer specific treatments and so on. But let me talk about ortho and parahydrogen. Last 10 minutes. आपकी समातों को मैं थोड़ा सा और झंझोड़ूंगा. आपकी 5 मिनट.
5 मिनट होने चाहिए, 10 मिनट में मसला हो जाएगा.
अब देखो ऑर्थो और पैराहाइड्रोजन को समझना बड़ा जरूरी है. हाइड्रोजन क्या है? हाइड्रोजन मॉलिक्यूल डाई एटॉमिक मॉलिक्यूल है, ठीक है. अब जो टोटल वेव फंक्शन है इस मॉलिक्यूल का, उसके बोन ओपन हाइपर अप्रोक्सीमेशन देखें. उसका एक ट्रांसलेशनल पार्ट है, वाइब्रेशनल पार्ट है, इलेक्ट्रॉनिक वेव फंक्शन है ग्राउंड स्टेट में, न्यूक्लियर स्पिन वेव फंक्शन है और रोटेशनल वेव फंक्शन है, ठीक है. और ये पूरे का पूरा वेव फंक्शन हैज टू बी इवन और ऑड under the exchange of electrons. It has to be odd because electrons are fermions. Agreed? Now all of this has to be odd. अब जो मैंने ब्लू में जाहिर किए हैं ना, ग्राउंड स्टेट में सारे के सारे इवन है, ठीक है. ट्रांसलेशनल भी इवन है कि अगर ये हाइड्रोजन का मॉलिक्यूल ट्रांसलेट कर रहा है, if you interchange or do a 180-degree rotation, the translation remains the same. ग्राउंड स्टेट भी इसका इवन है, वाइब्रेशनल स्टेट भी इवन है, ठीक है. ये वाइब्रेट कर रहा है, इट डज नॉट डिपेंड अपॉन इंटरचेंजिंग द. अच्छा, अब न्यूक्लियर स्पिन और रोटेशनल वेव फंक्शंस है ना, इनका प्रोडक्ट ऑड होना चाहिए क्योंकि इन बाकी तीनों का तो इवन है. अब न्यूक्लियर स्पिन और रोटेशनल वेव फंक्शन ऑड होने चाहिए, इनका प्रोडक्ट. अब देखो न्यूक्लियर स्पिन वेव फंक्शन है ना, वो 4 तरह के हैं. 3 ट्रिपलेट स्टेट्स हैं, एक सिंगलेट स्टेट है. जो एरोस का मतलब अल्फा बीटा. ये पढ़ा होगा पॉली एक्सक्लूजन प्रिंसिपल या क्वांटम केमिस्ट्री में, नहीं पढ़ा? सिंपली बात है, कोई बात नहीं, वीडियो खत्म हो जाए तो. ये देखो अल्फा अल्फा तो समझते हैं ना, न्यूक्लियर स्पिन वेव फंक्शन है, जेमन स्टेट है, ठीक है. अल्फा और बीटा 2 स्टेट्स हमने देखी ना ब्लॉक्स किए थे. ये पहला हाइड्रोजन एट न्यूक्लियस, ये दूसरा हाइड्रोजन न्यूक्लियस. अब इनको इंटरचेंज करें, इन दोनों न्यूक्लियसेस की आइडेंटिटी को, न्यूक्लियाई की आइडेंटिटी को. आप एक ऑपरेटर ऐड करें, पैरिटी ऑपरेटर को इंटरचेंज करके क्या मिलेगा? अल्फा अल्फा. तो दिस इज एन इवन वेव फंक्शन. व्हाट अबाउट बीटा बीटा? Even. What about alpha beta? Interchange beta alpha. This is neither even nor odd. ठीक है? So instead of taking alpha beta, you take alpha beta plus beta alpha under root 2. There is nothing special about alpha beta. You can make a superposition. Now if you apply the parity operator, interchange alpha beta, you get beta alpha plus alpha beta, which is the same as the original. So these 3 kinds of states, alpha alpha, alpha beta plus beta alpha and beta beta, they are called the triplet states. They are even under exchange. The 4th kind of state is called a singlet state. Singlet का लफ्ज़ तो सुना होगा ना आपने? अभी जो सिंगलेट स्टेट है, ये न्यूक्लियर स्पिन्स की बात हो रही है। ये जो सिंगलेट स्टेट है ये ऑड है अंडर इंटरचेंज। ये अल्फा बीटा माइनस बीटा अल्फा विल बिकम, they will get a minus sign after interchange. So there are three kinds of even nuclear spin wave function and one kind of odd. अब देखो जब हम कहते हैं ना, एग्जांपल देता हूँ आपको समझ आ जाएगा। एक ऑर्बिटल के अंदर दो ही इलेक्ट्रॉन हो सकते हैं बिकॉज ऑफ द पॉली एक्सक्लूजन प्रिंसिपल। उनके स्पिन्स एंटी अलाइन होने चाहिए। तो दो स्पिन्स आर इन दिस स्टेट अल्फा बीटा minus beta alpha. They are in the singlet state, or they could be in the triplet state as well. Alpha beta plus beta alpha. ठीक है? So you have a linear combination of these states. Anyways, there are four kinds of nuclear spin wave functions. Any nuclear spin wave function of the two hydrogen in the molecule can be represented as a combination of these four basis states. अभी तीन है इनमें से even, एक है odd. The triplets are even, the singlet is odd. All right. So we know the four nuclear spin wave functions. What about the rotational wave function? अब एक rotational quantum number है J. ये पढ़ा? J 0, 1, 2, 3, 4, 5, 6 हो सकता है. The rotational quantum number. Agreed? Now when J is 0, 2, 4, J is even, the rotational wave function is even, and when J is odd, the rotational wave function is odd. अब हमने न्यूक्लियर स्पिन और रोटेशनल वेव फंक्शन को, इनके प्रोडक्ट को ऑड करना है। इसका मतलब ये है कि जब J 0 के बराबर है, रोटेशनल वेव फंक्शन इवन है, न्यूक्लियर स्पिन वेव फंक्शन ऑड होगा, ताकि इन दोनों का प्रोडक्ट ऑड रहे। जब J 1 स्टेट, J क्वांटम नंबर 1 है, जिस तरह L है ना ऑर्बिटल क्वांटम नंबर, पूरे मॉलिक्यूल की रोटेशनल क्वांटम नंबर J है। जब J 1 है यानी रोटेशनल वेव फंक्शन ऑड है, इसको लामहला नेसेसरली इवन होना पड़ेगा ताकि इनके प्रोडक्ट को ऑड रखे एंड सो ऑन। अब हाउ मेनी टाइप्स ऑफ ऑड न्यूक्लियर स्पिन वेव फंक्शंस वी हैव? 1 and 3 kinds of even. If we can force the quantum state to be odd, the nuclear spin state, somehow, then we will have all the hydrogen atoms, all the hydrogen wave functions in the same quantum state. कहने का मतलब ये कि अगर हम किसी तरह ये जमानत दे दें कि हमारा रोटेशनल वेव नंबर 0 होना चाहिए, तो लामहला या necessarily rotational wave function will be even and nuclear spin wave function will be odd.